go back.
All right, so for the final talk of the day, it's a great pleasure to welcome Joel Kamnitzer from Toronto, who will be, I don't remember what the title is, but that's all right.
I think something like Categorical G-actions and Truncated Shifted Yangians. Okay, thank you for the invitation. Can everyone hear me well? I'll take that as yes. Okay, so let's begin. So let's say I'll start with G, a semi-simple Lie algebra. Please let me know if there's something you can't read or hear. And in this talk, we'll be interested in tensor products of irreducible representations of G. So I'll write V of lambda with an underline to denote the tensor product of such irreducible representations, V lambda 1, V lambda n. So lambda i's are dominant weights. And of course, this tensor product representation has a decomposition into weight spaces, V of lambda mu. Now, what's the problem we're going to study? It's a kind of familiar problem, let's say, is categorify V of lambda. So what does that mean? Well, so 15 years ago, when I was in my last year of graduate school, 15 years and a few months ago, I visited Koulomb and Davis, and he kindly spent about 2 hours talking to me about this nature of this problem. And here's what he said. So we want to find categories. I'll call it C of lambda mu, maybe abelian categories or triangulated categories. And well, what's properties of this categories? We also want to find functors. So these categories should come with some natural functors. We'll call it EIs, and functor in the opposite direction, maybe an adjoint functor, FIs. You go like this, and what should be true, the growth in the group of such a categories should be isomorphic to the corresponding weight space of our tensor product representation in such a way that EI becomes the action of the usual Chevalier generators of our Lie algebra. Becomes little EI in G. And similarly for FIs. Okay, so, and maybe also you might ask for commuting actions of a braid group, especially if you're interested in finding non-invariants, but I'm not going to talk much about, well, at all about that aspect today. So just talk about this problem of categorifying a Lie algebra representation. So this is roughly speaking how Koulomb explained it to me 15 years ago, and people have worked a lot on this problem and in some sense have solved it. So let me outline the solution to this problem. So let's say this is due to Koulomb Lauda, Ruquier, and Webster. Well, maybe others too, but let's stick with these people. So they defined a family of algebras, which sometimes people call Webster's tensor product algebras. I'll call them KLRW algebras, denoted T lambda mu. They're diagrammatic algebras. So the elements in the algebra are certain diagrams that look something like this. There's some red strands, that's the squiggly guys. There's black strands, those are the white ones. There's crossings, something like this. And the red strands are labeled by these lambdas, the sequence lambdas. This red strand might be lambda 1, this red strand might be lambda 2. And the number of black strands is determined by lambda minus mu. Number of black strands, they're labeled by the Finken diagrams, the number of blacks labeled I times alpha I is equal to lambda minus mu. And here lambda, by the way, is the sum of all those lambdas. Okay, so this is the elements in the algebra. There's some relations, and there's a multiplication as usual is by concatenating diagrams. I won't go into the relations, but maybe one relation is that if you have a diagram has a leftmost strand black, then it's 0. And in particular, if this sequence lambda only consists of one element, so it's just, and this n that I defined as 1, there's only one thing in this sequence, then this algebra is nothing but a cyclotomic KLR algebra. Okay, so what did these Kovanov, Ruki, and Webster, and so on do? They constructed functors, EIs and FIs. I'll just write EI just for simplicity. So between categories of modules over these algebras. And this has to do with well, adding. So when you add alpha I, that corresponds to deleting one strand, one black strand labeled I. So that's what this functor does, somehow relates to algebras where we've reduced the number of black strands labeled I by 1. It's a kind of restriction functor, and then there's also a corresponding induction functor. So these are functors, and they proved that, well, that this gives a categorification. So the growth in the group of the category of modules for these algebras is isomorphic to this weight space, and compatibly with these functors become the Chevalier generators of the algebra. So that's the work of, that's the algebraic solution to my problem, to the categorification problem. Okay. So you might say story's over, but we're interested today in somehow geometric solutions of the categorification problem. So let me erase the board. Then we're going to discuss geometric solutions. Oh, erasing the board takes always a little longer than I think it should. Okay, there we go. So for geometric solutions, we begin with Nakajima covarieties. So we have some Nakajima covarieties. Which I'll denote by M lambda mu. So it's a little different than Nakajima's usual notation with a V and a W. And how is it defined? Well, you start with a representation space, I'll call it R lambda mu of a quiver. You take its cotangent bundle and take the Hamilton, the algebraic symplectic reduction by a product of general linear groups. So I won't get into too much detail, but just as a little picture, here we have framed quiver of type G, and here's the framing, and the framing dimensions are determined by lambda, and the gauge dimensions, these VIs, are determined by lambda minus mu, as before. And R lambda mu is like the space of all linear maps for this in this quiver. So this is this Nakajima quiver variety, which is closely related to this weight space in this tensor product. For example, the cohomology of this Nakajima quiver variety is isomorphic to this weight space. Well, this might be true if all these lambdas are fundamentals. If it's a little more complicated, maybe if lambdas are not fundamentals, but something similar. True. So now we have the following theorem of, again, many people. So let's say Ruquier, Webster, and Varignolo Vassereau. So the theorem is that this T lambda mu, this diagrammatic algebra, is an X algebra between semi-simple perverse sheaves in category of derived category of equivariant constructible sheaves on this representation space of the quiver. And kind of the upshot of this fact that it's an X algebra is that this category of modules is pretty closely related to the category O for the quantization of this quiver variety. So more precisely, Ben Webster proved that this category of modules is quadratic dual to this category O. Dual to category O for the quantization of this quiver variety. Okay, so this is a little bit, I realize, a little sort of not too detailed explanation of this quadratic duality and this category O, but I'm just trying to set the stage for where I'm going in the talk. This is a little bit just as kind of background. I won't need the details exactly of this part. And moreover, this, let me explain that this, in this quadratic duality, we just described a minute ago that there are some functors between these category of modules corresponding to our Chevalier generators. so this functor, EI functor here, then we have this quadratic duality relation between this category O for Nakajima core variety, and then here quadratic duality for category O for the other Nakajima core variety. And this is a kind of commutative diagram where here, this functor is quite easy to describe. This comes from correspondence. So kind of a natural correspondence between the two quiver varieties. Correspondence defined by Nakajima. So I'm emphasizing that this diagram commutes, and it's not kind of complicated what goes here on the right. It makes sense. It's easy to see what goes on right here. Okay, so now let's move to, this is kind of not the main thing I'm talking about though today. I want to talk about a different geometric incarnation. So there's another geometric incarnation. Another geometric incarnation. And the origins of this other geometric incarnation, either you can say comes from the geometric Satake correspondence, or you could say it's related to Nakajima core varieties by symplectic duality. Okay, so this other geometric incarnation is called affine Grassmannian slices. So another geometric incarnation of these weight spaces in tensor products is affine Grassmannian slices. Slices, they're denoted W lambda mu. And here's their definition. So we need to work inside the affine Grassmannian of G. So let me just put that over here in affine Grassmannian, actually of the Langland's dual group to G. It's not very important at the moment. So this affine Grassmannian is I take the quotient of G check over Laurent series by G check over power series. So that's my affine Grassmannian. And what do I do inside this affine Grassmannian? I consider a certain intersection. This W lambda mu is defined to be an intersection of the following two things. I take the spherical Giobo orbit, so that's defined like this, through T lambda, take its closure, and then I intersect with the transverse orbit of this group, G1 T inverse, through T mu. Okay, so here this G1 guy is the kernel, G1 T inverse is the kernel of this evaluation map from GT inverse to G. We'll check it for, I suppose. Okay, so that's the definition of this gadget that I'm going to study a lot, affine Grassmannian slice. And actually, surprisingly, this is actually only the definition if mu is dominant. If mu is not dominant, there's a nice definition, there's a nice generalization of this affine Grassmannian slice, but it is a bit more complicated, and I won't define it here. Okay, so this is when mu is dominant. And what kind of beast is this affine Grassmannian slice? Well, it's an affine variety, so it's like an intersection of a kind of Schubert variety with an opposite Schubert cell. So it's an affine variety, and its dimension is given by you take the difference between lambda and mu and pair that against rho. That's and multiply it by 2, pair it against twice rho. That's the definition of this W lambda mu. And moreover, it carries a natural Poisson structure, W lambda mu. So as it carries a natural Poisson structure, it's nice. It's interesting to think about its quantization. So quantizing a Poisson variety means to find a non-commutative algebra whose associated graded is isomorphic to that Poisson variety, the coordinate ring of that Poisson variety, where the first order of the non-commutativity is given by the Poisson bracket. So this idea of quantizing these affine Grassmannian slices was first carried out or thought of well, almost 10 years ago now with Webster, Weeks, and Jacobi. So we introduced a family of algebras called the truncated shifted Yangians. So we have these truncated shifted Yangians. They're denoted y lambda mu. So I'm not going to give their definition, but it's something that's actually defined, something you can really work with, something defined by actually a presentation, by generators and relations. More precisely, it's a subquotient of the Yangian. So shifted Yangian, this is a subalgebra of the Yangian, and then truncated means you take a quotient. Well, only for mu dominant is actually a subquotient of the Yangian. In general, it's not a subquotient of the Yangian, but even for mu not dominant, still something you can really work with. And so it's a non-commutative algebra with a filtration. And we proved, well, actually, we sort of give most of the proof and then the final step in a different paper. So this is due to Self, Webster, Weeks, and Jacobi, supplemented by a further paper of Braverman-Finkelberg and Nakajima. So the theorem was that this does quantize. So the associated graded of this algebras is isomorphic to the coordinate ring of our affine Grassmannian slice. So I guess I should mention that this affine Grassmannian slice is closely related to this weight space in this tensor product representation. In fact, if all those lambdas, if all lambda j's are minuscule, then it's exactly true that the cohomology of this affine Grassmannian slice, W lambda mu, is isomorphic to this weight space in the, weight space in that tensor product representation. And so for this reason, and because of this symplectic duality motivation, it's natural that we should try to use these algebras, y lambda mu, to categorify this weight space. And in fact, that's what we did. So from 2 years ago, with, well, almost the same people, but plus Peter Tingley, we proved that there is an equivalence of abelian categories between this category O for this truncated shifted Yangian and this T lambda mu mod, this KLRW algebra. To be a little bit more precise, this algebra is not just one algebra, it's actually a family of algebras depending on a parameter. So depending on the value of that parameter, it affects exactly the sequence lambdas which add up to this lambda. Or even more generally, you might not get, we define some generalization of these KLRW algebras, which exactly depend on the same parameter. So it's slightly, the statement is slightly more, actual statement is slightly more complicated. But I want to emphasize it's really an equivalence of abelian categories. And in fact, the equivalence is very direct. Like you take a module here and you do something and produce a module here, and it's totally algebraic. You just by some explicit generators and tricks with the elements, you go back and forth. I mean, no one, but it's motivated from somehow, well, this equivalence is kind of, and the construction of it is motivated from this general perspective of this Braverman-Finkelberg-Nakajima's perspective of this Coulomb branches. Okay, so something I'm not going to talk about much, but maybe it's a good time to mention it, is that this W lambda mu is what's called a Coulomb branch. It's a Coulomb branch related to the same gauge theory that produces the Nakajima quiver variety. And this quantization, this truncated shifted Yangian, is a Coulomb branch algebra, a non-commutative algebra from this Coulomb branch construction. And this Coulomb branch perspective somehow underlies this equivalence, the idea of this equivalence. Okay, so we have this now with this equivalence. Well, in fact, from, as I mentioned, from 2 years ago. So one can consider the following diagram. We have category O. So I'll just write the algebra and then an O to denote its category O. Equivalence of abelian categories with T lambda mu mod. We have this restriction functor EI for these KLRW modules, the one which corresponds to getting rid of the ith one strand labeled I labeled black strand. And now another equivalence here. And then one can ask, what functor goes here? So how can you construct a functor between these two categories, making this diagram commute? So, fill in this diagram. And what makes this harder than you might expect is that the corresponding varieties, so here we would be looking at the variety W lambda mu, and here the variety W lambda mu plus alpha I, they don't really obviously talk to each other, right? Because this one, like they don't sit inside of each other, certainly, because this one is like a slice at this mu plus alpha I, and this is a slice at mu. So they're disjoint from each other. And moreover, there's not any natural correspondences between these two guys. There are natural correspondences from this thing to itself, but those natural correspondences are related to the braid group action. So you can use those correspondences to cook up a braid group action on the derived kind of coherent sheaves on this guy or on modules over this quantization. That's what I did with Cottis for many years, basically. I mean, it's slightly different in language, but basically it's what I did with Cottis. So those correspondences are used for this braid group action, but for a correspondent, there's no natural correspondences that go between these two different varieties that one could use to construct this functor. That's why this is different than the situation with the quiver varieties that I talked about a few minutes ago. So that's why this is like kind of non-trivial question. And another thing that's kind of makes it non-trivial is that this relationship between this affine Grassmannian slice and this weight space comes from the geometric Satake correspondence, and the geometric Satake correspondence is like notoriously inexplicit. So if you were to sort of understand this functor as some kind of categorification of this geometric Satake action, and this geometric Satake action is itself kind of a mysterious thing, so categorifying it is like, you know, doubly mysterious. Okay, so anyway, so this is the problem I'm going to talk about today, and I guess I will take a break right now.
That's good timing. We'll reconvene at 58 after the hour. In the meantime, please ask questions. There's one question already in chat for you, Joel.
I kind of lost my chat thing.
Unless Nito wants to ask it himself again.
The guy I'm looking at now.
Can you see the question, or do you want me to repeat it?
Automorphic set, spectral set. So basically you're asking kind of if there's like a Langland's kind of duality explanation of this relation between the quiver variety and this affine Grassmannian slices.
Exactly.
I don't think that's true. I can't, yeah. I've never, as far as I know, it's not the case. But yeah, I don't really have any better answer. As I mentioned, the relation. As I mentioned, the relation between the quiver. There's this general perspective called symplectic duality, which has been also known as three-dimensional mirror symmetry, which has been a very popular topic in the past, say, 5 to 10 years, and that really is the general framework, which encompasses this relation between Nakajima varieties and affine Grassmannian slices.
And this is the Coulomb versus Higgs.
Also called Coulomb-Higgs branch, yeah.
Got it. Okay, so the quiver variety is a different side of that duality.
Yeah, quiver variety is the Higgs branch, and this guy is the Coulomb branch, yeah.
Is it easier to construct the braid group action on this side than it is on the other side, or is it just as obvious? Is it just as easy on the other side?
No, it's easier here. I mean, you know, depends what you mean by easier, but yeah, I would say it's easier here. Another way of saying it is that if you look at you know, Ben's construction of the
I have looked at it.
and if you try to pass that into this geometric land, pass that into this quiver land, I don't know. Well, Ben probably knows what it is, but I think it's not so simple at all there. Like, again, it's not like the G action here, it's not coming from a quantization of some natural correspondence. So somehow you should think what I'm doing now is like on the same level of kind of difficulty as Ben's construction. Well, the same difficulty as the geometric realization of that construction for right then. In fact, it's not just in type A we have this how duality, which is actually swapping the affine Grassmannian slices and the Nakajima curve varieties, and actually kind of swapping this, well, internal categorical G action with the external commuting SLM action. As people know, I like this story a lot. And so there's actually even a strong statement you can make about the fact that the relation between those two things.
Sorry, is it related to this twisting and shuffling functors that like Braden, Proudfoot, at Webster consider?
Yeah. Yeah. So I always forget who's who, but on either for, if you're interested in this braid group action that leads to non-invariance, commuting braid group action, on one side it's given by twisting functors, and the other side it's given by shuffling.
But your correspondences that, or like your functors that you're about to construct, they're examples?
They're not. I mean, they're not directly related to those things because they're not twisted or they're not twisting or shuffling functions.
Because they're for different varieties, I guess, right? So they go like from one to another.
Yeah, and because they're not give a braid group action, they're going to give this, as you know, the Lie algebra.
Yeah, because they go like from one space to another, I see.
Yeah, yeah.
But more really like the relation between them is again some kind of like twist and shuffle.
Yeah.
These correspondences are, I guess, whatever, twisting. And I don't know.
Yeah, I don't know.
Okay, whatever.
Should I resume then, Ben? Or?
Yeah, that was good. You can resume.
Any other question? Okay. Just give me that thingy. Okay.
So is your construction in general, like, you know, in simplest case gives you Nakajima action of the Heisenberg algebra on Hilbert scheme of points on C2? So that is it included somehow in your construction?
Well, that would be like the one I started, the thing I started talking, like toward the beginning, I talked about this G action on the Nakajima curve varieties. And yes, a special case of that would be the Nakajima's action on the Hilbert scheme. But now I'm talking about this other geometric incarnation using affine Grassmannian slices. And, but in particular, since these Hilbert schemes are sort of self-dual, it would be something about some kind of action probably of this Heisenberg on the Hilbert schemes, but not coming, again, that action of Nakajima on of the Heisenberg on the cohomology Hilbert schemes, that comes from natural correspondences. And again, what I'm talking about now, or about to start talking about, doesn't come from correspondences. Natural course, I mean, it comes, as you'll see, it's maybe does come from some correspondences, but not from like the obvious correspondences. So yeah.
Great. Take it away, Joel.
Okay. So so we're trying to relate W lambda mu and W lambda. So I'll just get back to the noise. So I want to relate one affine Grassmannian slice and another affine Grassmannian slice, or perhaps instead of just the slices, the corresponding algebras. Okay. So how are we going to do that? Well, actually, I don't have a complete solution to my problem that I posed, but I actually have, well, I kind of have two sort of answers. So I'll give you both answers. So here's the first answer, which has a nice geometry behind it. Okay, so we can define an action. So we define an action of the additive group. So GA just means like the complex numbers under addition on this affine Grassmannian slice in the following way. Well, it's not too complicated. If we just have A, that's an element in the complex numbers, acting on G. So G is an element in this affine Grassmannian slice, thought of as a element of the group over the power series. And what are we going to do? Well, we're just going to multiply this element on the left. Sorry, thought of as an element in the quotient. In that figure. I'm just going to like multiply this guy on the left by just xi of a. What's xi of a? It's just the embedding of c into g. So I guess g check to be more precise. Given by this I. So I never said what I was. So I'm going to find not just one action, but one action for each alpha. So here alpha I is a choice of simple root. I guess it was fixed above. Okay, so I maybe fix this choice of simple root for now. And I have this ith embedding of the complex numbers into G, and I just use that left multiplication by the thing to define an action of GA. So why might this be useful? Well, it turns out this variety is, if you just look at the formula I gave for the dimension in the beginning, or I said out loud, this variety is two dimensions. Its dimension is 2 less than the dimension of this guy. So if I can take the Hamiltonian reduction by this group on this guy, I do get something of the right dimension. And that's precisely what we'll do. So here's a theorem. So this is not yet on the archive, but will be hopefully in a couple of weeks, almost done. So this was my student Koa Pham and well, my former student Alex Weeks. So there's an isomorphism. Between the Hamiltonian reduction of W lambda mu by the action of this GA at the moment 1. So what it means is I take this moment map, phi I, for this action, I take the inverse image of 1 and divide out by the action of GA. Sorry, that's just the definition of the thingy. And here's the isomorphism. It's isomorphic to the smaller variety. So again, I mentioned this guy's 2 dimensions smaller, and when you do this Hamiltonian reduction, dimension goes down by 2. So that's great. In fact, this isomorphism is actually pretty easy to construct. I mean, I was going on about there being no natural relations between the 2 varieties, and here I just made a natural relation, and actually the relation is not so hard to find. It works like this. So there's actually a map from, I'll call it W0, sorry, 0 minus alpha I. So it's this, I've mentioned that this W lambda mu, I've sort of been only advertising it sort of when mu is a weight of this lambda representation, but you can define it more generally. For example, there's even a W0 and then some things down here. So there's this thing as W0 minus alpha I, and there's a map, natural map like this given by kind of a multiplication inside my group. It goes like this. This multiplication map. And this thing actually gives an isomorphism with the inverse image of C star under the moment map inside of W. So that's actually an isomorphism. And then from this, you can prove the Hamiltonian reduction statement. So you can prove this isomorphism as a simple consequence of this isomorphism. And it uses, well, to prove it, you also need to know that this guy is just the cotangent bundle of C star. Okay. So actually not so bad to construct this isomorphism to relate these 2 guys and with this Hamiltonian reduction. And in fact, there's a quantized version of this isomorphism as well. So the quantized version would be that, well, I'll just focus on this latter thing. So this inverse image of the moment map of C star translates over to, it's a on the level of functions, it means we're inverting the moment map. So on the quantized level, we're inverting a certain element in the quantization. That element happens to be called EI upper 1. So I invert that element, and there's an isomorphism between y lambda inverted that element and a tensor product here, corresponding to the algebras which quantize these guys. So that's a second theorem. And the map from the left actually goes from right to left is given by co-multiplication, a kind of a co-multiplication map for these truncated shifted Yangians. And such co-multiplications, multiplications were introduced a couple years ago in my work with Finkelberg. I'll just give him an F. Let's see if you're ready. Finkelberg, self, Rybnikov, sorry, Pham, Rybnikov, and Weeks. Okay. So we studied these co-multiplications, and then just now we proved that that we have an isomorphism like this, quantizing this isomorphism, and then you can make some kind of non-commutative version of this statement as well. This thing is still a little bit in progress, and I'm not so sure we'll actually be able to prove this in full generality, but at least it's true in type A, and there's a sort of slight weaker result in general. I won't get into that. Okay, so that is one relation between these algebras, this algebra and this algebra that we wanted. But unfortunately, while I do like this relationship, I don't know how to use this isomorphism to construct the functor that I wanted in that commutative diagram on the previous board. So I wanted that commutative diagram related to between category O over here and category O over here, a functor between these two category O's. And you might think that this isomorphism gives you a way to construct such a functor, but haven't managed to do it yet. So it may be possible. I'm not saying it's impossible, but at least naively it doesn't quite seem to work to make that diagram fill in. So that's kind of the end of this route. But then there's another route, which I'll explain now. The other route is like a little more complicated. That's why I did this one first. So in the other route, rather than directly building an isomorphism like this, we're going to build a kind of more complicated chain linking this guy with this guy, or actually even with this tensor product. So the more complicated chain is, first there's another algebra. I'll call it, okay, so let me just write this down, more complicated route. The advantage of this more complicated route is it really does allow you to build a functor which fits into that diagram that I mentioned before. So how does this more complicated route go? It starts with an algebra called, well, for the purpose of this talk, I'll just write like this. So it's a certain matrix algebra, over y lambda mu. And then there's an embedding from this matrix algebra into, embedding into this matrix algebra of some other algebra, which I'll call, it's almost the same, so I'll just put a prime on it. So it's some subalgebra of this matrix algebra, but I tend to think of them as almost the same thing. So an embedding of this subalgebra, so I have some subalgebra of this matrix algebra, and then the final step is an isomorphism between a localization of this funny subalgebra and this guy on the left side. Sorry. So much as in the theorem above, I have here I localized my original algebra by some element, and I got this tensor product. And here I started with my algebra, construction matrix algebra over it, found some subalgebra of that guy, localized that guy, and then I got that thing. So it was way more, that's why it's a more complicated route, but somehow in the end, it's not, the answer is looks kind of the same. But the advantage of this more complicated route is that it allows us to define a functor. So, okay, I guess I have to erase now. Maybe it was a slight mistake, but Okay, how about I leave this guy here? Erase this part. Okay. There's the more complicated root left down below. Now let me explain how we use the more complicated root. So to use the more complicated root, we construct a functor. So first we have this Morita equivalence. So we have this Morita equivalence with this algebra, this matrix algebra. So that's Morita equivalence. Then we just restrict to this subalgebra. Then we do this localization. So invert this element R, invert this element R in our module, and then use this isomorphism. Then we go to here. So that's a sort of multi-step procedure, but somehow, even though it's a multi-step procedure, it's actually it's easy to control. Somehow the reason why this thing is better behaved than the isomorphism I talked about a few minutes ago, which a priori looks simpler, is the isomorphism I mentioned a few minutes ago does something complicated on the Cartan, whereas every step in this chain does a very simple thing on the Cartan part of this truncated shifted Yangian. So because it's doing something very simple in the Cartan, you can understand what it does on weight spaces, and things are well behaved. So then we have the following theorem. So this is back with the old gang of Webster, Weeks, and Jacobi. And so these combining together these functors, this gives a functor from the category O for y lambda mu to the category O for y lambda mu plus alpha I. And this making the diagram that I mentioned a few minutes ago commute. So let's put that diagram back up. So this diagram that I mentioned before, well, now it's going to be turned on its side, but anyway. So here is the equivalence with this KLRW algebra. Here with this is KLRW algebra. And here is this usual functor from the world of KLR algebras related to deleting the black I strand, and this diagram commutes. This diagram commutes. Okay, so I guess I still have a few minutes. Shall I continue? I have something else to say, but I can either stop or say something else. But since I have
I mean, there's a question in chat if you want to answer it, or if Alexa wants to say it aloud. Now's a good time for it.
Yeah, good time for questions. Do you want to ask your question?
Okay, I put it in chat, but I can repeat it. So the construct this complicated root looks like this induction functor in this atomic Cherednik algebras, and people use this stuff to categorify also this, SLN.
Yes, yeah.
Relation.
Yeah, in fact, we do think this is related to induction restriction functors for Cherednik algebras. Yes, should be related.
Okay.
Yeah, and we should have a theorem about the relation in our paper. But I don't know enough about that story to state anything precise now. But yes, it is related.
All right, thanks.
Is there like any understanding on like this functor y0 minus alpha I tensor, you take iterates of this functor and look at its natural transformations. Is this some Webster-like algebra, or am I confused?
Yeah, well, if you
I guess everything there's some read equivalence going around.
no, well, if I mean this functor I just this functor I just defined as like kind of like the e, it's like this ei as I mentioned. If you take kind of iterates, if you want like ei nth power, there's a natural way to do that in this theory, and in fact you do see the action of the in the morphisms of ei to the n should be the nil affine Hecke algebra, as you know. And you do see this nil affine Hecke algebra appearing here, yeah, in a natural way.
Cool.
Okay, so I guess what's not clear, right, is why. So I mentioned these funny algebras. This funny algebra, well, it was just a matrix algebra, and this funny algebra, which was a subalgebra over this one. And you might ask, where do these guys come from? So let me explain that now. So to explain where they come from, we need to explain. I need to go back a little bit and say about a little bit of this Coulomb branch story. So Coulomb branch story. So imagine I'm like starting my talk over again or something because I want to use the letter G again. So G here is a group unrelated to the G I had before, just another reductive group. In fact, usually for me, this G is actually just a product of GLNs, kind of one for each vertex of my Dinkin diagram of the original group. So G is some reductive group. And let's say V is a representation of G. And I'm going to fix one more piece of data, which is a parabolic subgroup of G. And Braverman-Finkelberg-Nakajima have defined a Coulomb branch. Branch algebra. So let me just skip straight to the algebraic version. So it's an algebra, non-commutative algebra. I'll call it AGV. In fact, it comes with some kind of parameter h bar, and when h bar is 0, it becomes a commutative algebra, and then you can take spec of that commutative algebra, and then you get a Coulomb. Then you get the Coulomb branch, like the variety, which is the spec of that algebra, the h bar equals 0 algebra. Let me go straight to the non-commutative version. So non-commutative algebra, AGV. And like as a special case, when G is this product of GLVIs corresponding to the Dinkin diagram of G, and this V is this quiver representation space R lambda mu that you use to construct the quiver variety, that you use to build the Nakajima quiver variety, then this non-commutative algebra is precisely this Y lambda mu. Okay, that was a theorem in the appendix of second BFN paper, which was written jointly with Codera and BFN and Webster and Weeks. Okay, and another thing I wanted to say is that there's a parabolic version of this AGV, so which is called APGV. So this is always a matrix algebra over AGV. Let me just one word on how these things are made. So to define AGV, you start with the affine Grassmannian of G, and you construct on that affine Grassmannian an infinite rank vector bundle, and use that infinite rank vector bundle as an analog of the cotangent bundle of the flag variety, and you form a kind of Steinberg variety, and then you take the homology, and that homology of that kind of Steinberg-like variety has a convolution algebra structure. That's AGV, and for this AP version, rather than using the affine Grassmannian, you use some partial affine flag variety. And then you get some read equivalent things, so matrix algebra over AGV. So that's those guys. And then one more piece of data. Sorry. So one more thing I'll need is, well, the levy of this parabolic, L. So L is levy of the parabolic, and I also need C, an embedding of C star into G, into the torus inside of G, whose centralizer is this Levi. Okay, so the centralizer of this Xi is just the Levi. So you can imagine if you're in, well, G is like GLN, and this guy has like a block, equal blocks related to this stuff. Okay, so then we're going to relate the following algebras. So we have G and V, then we can consider A GN, A PGN, sorry, A AGV, A PGV, A LGV, and lastly, A LVC. So VC means the invariance in V for the action of this guy C, where C is this embedding of C star. And so these are 4 different algebras we can study given this data. So all of them are kind of versions of this Coulomb branch algebra. And these 4 guys are related as follows. Here's a theorem in our forthcoming work. That this, well, as we already know that we have a Morita equivalence. Equivalent to APGV. There's an embedding of a LV inside of APGV. They're almost the same thing. And if we take a LV, then there's a certain element called a monopole operator associated to this C element and map from C star into the torus. If you invert that monopole operator, it becomes isomorphic to A, L, V, C. And together, this theorem allows you to build a functor and study nice, that you can really get your hands on to study properties of this functor from modules for a GV, like for example, weight modules or category O, to this ALVC. And in our situation, so we have this, in our situations where we take, again, G is a product of these GLVIs, then this AGV is this algebra truncated shifted Yangian V lambda mu. C will be this embedding of C star into the ith copy of GLV, sorry, the GLVI, and it's given by just a map which takes some T to the matrix T111111. That's C. And for this choice of C, it's not hard to see that this A L V C is nothing but Y lambda mu plus alpha I. So this relationship between Y lambda mu and Y lambda mu plus alpha I that I was looking for is a special case of a more general relationship between the Coulomb branch algebra AGV and the Coulomb branch algebra ALVC. So I should say mod here, I guess. And in this way, this functor I was looking for is a special case of this more general functor that you can study. And those funny intermediate algebras I mentioned a few minutes ago are these 2 guys here, this guy and this guy. These are these intermediate algebras that I mentioned a few minutes ago. And that's where they come from, this Coulomb branch perspective. Okay, I guess I stopped there.
Great. Are there questions for Joel?
Maybe I'll leave the screen share on just in case there's questions about what's here.
I'll start things off. This parabolic version you say is just Morita equivalent, is just a matrix algebra, but is there some like other thing acting on this natural and factorial bundle or whatever? Like, is there a commuting thing for which is a more interesting bimodule?
Not that I'm aware of. Like its main purpose is to admit this embedding of this LV into it, somehow. I don't know any like deep explanation about it, but you just wouldn't be able to do this kind of theorem if you didn't have this APGV here.
And You describe a functor from like G to L. Is there a one back? I mean, like, I guess you can induce and restrict along this.
Yeah, so I've sort of been focusing throughout the talk on like the EI functor, but there's every time I wrote a functor, you can always study its adjoints, and like if you work, especially if you work in this categorical world, then the two adjoints will be related by a shift.
But this is more of like an E and an F thing rather than like a sort of Zergli-Hecke thing, or is it? I guess it's really both.
Yeah, I would say it's more E and an F thing. Yeah.
All is quiet on the Western Front. In that case, let's thank Joel again.